the behavior of fish that swim together in a group and maintain a tight formation with the same speed and direction. This is not to be confused with shoaling, a similar behavior where fish hang out loosely in groups without a general direction. So what's different about our simulation model when compared to this existing model? Our model has two features that stands out. First, the predator. The predator will promote evasion behavior in fish, as well as show how schooling increases their survivability. And second, the food. The randomized food zone in simulation will give purpose to the fish to scatter out and approach specific location as school. This also encourages a more natural behavior. Here's the comparison to the existing model. As shown, our model is not only exhibit fish schooling behavior, but also food foraging behavior and predator evasion behavior. Now, let's talk about the background. The question is, how can we simulate the behavior of fish? In previous models, the three-rule model is used. This is a classic approach to modeling the individual behavior of animals in a flock, herd, or school. It composes of these three rules. Collision avoidance, which motivates individual to avoid collision with other members. Velocity matching motivates individual to keep the same velocity as other members. And flock centering motivates individual to stay close to the center of the community. Another method is to use black box modeling, which relies on machine learning algorithm. The black box model can be more complex and thus require close observation for unwanted results during the development process. Our project will make use of the deep reinforcement learning algorithm. This is the same machine learning method used in Google AlphaGo, which is a Go-playing AI who has overcome the world champion in set game. Next, let's take a look at our design requirements. The most critical requirements, those that will not complete the simulation without them, are the simulation must include 4 types of objects: fish, food, obstacle, and predator. Fish must control using a machine learning algorithm, and fish must exhibit 3 behaviors: schooling, foraging, and evasion. The other 2 requirements allow the user to observe the simulation more clearly. Those are, the simulation can adapt to changes made by the user. For example, if the user relocates an obstacle, the fish should adapt and avoid the obstacle in its new position. And the quantity of fish in the simulation, at least 2 are required to show that the fish can form a school. But preferably at around 30 is where the behaviors start to become more apparent.
Okay, so now for the environment design, the map that the fish will swim in is a 2D square map. And in the center of this map will be the spawn zone. In the initial state, agents or our so-called prey fish will spawn at random points with random directions within this spawn zone. And other than the spawn zone, there will be 2 food zones spawn randomly within the map. And how this food zone works is that in these food zones, there will be fixed amount of food balls spawned at random points within this food zone. And these food balls can be eaten by our agent fish on collision. The food zone will always have the same number of food ball density, which means that this food zone will always maintain a constant number of balls that are present at a certain time. And the number on the top right corner here is the total amount of food balls that is left in this food zone. This means that maybe there can be 8, the number of density of the food ball may be 8, but the total number of food balls is 100. So fish agents can eat food balls in this food zone 100 times until the food balls run out. And when these food balls run out, food zones will respawn at another location with maximum food count replenished. As you can see here, it became 100 out of 100. And you may be curious why we do this. Moving food zones will encourage agents to explore the entire map. So each time each food zone runs out of food, it will spawn from here to maybe here to encourage agents to not stay in just one location. Okay, next, for the agent design, our agent or prey fish has 3 major properties: its velocity, its position, and its radius. An agent has a radius as a property because the physics engine that we use in Unity, we actually chose a circle hitbox for the agent to minimize the calculations needed for collision so that we can actually run the simulation with more agents. And next, for the agent movement, agents have 2 ways to move: steering left and right, or accelerating and decelerating. Fish speed is also capped to a positive range of minimum speed and maximum speed. The value that we use here is the maximum speed is 2 times the minimum speed. And agents have to see the world, right, for them to navigate it. So they have 2 main ways to see the world. The first way is raycasting. In raycasting, they can observe 2 types of objects: food and obstacles. And in radar scanning, using radar scanning, agents can observe neighbors and predators. Whenever neighboring agents or the predator swims inside a certain agent's radius of scanning, that agent will be able to know the location and speed of their neighbors or the predator. Now, we know that the agent can see food. It can also see obstacles in walls. It can also see its friend, and it can also see maybe a shark. So with all these information, how does it decide where to swim to turn left or to turn right, to speed up or to slow down? To make the agent be able to make these decisions, we use what is called a neural network. In this neural network, or the brain of the fish, we have a total of 194 inputs to put into this brain, right? These 194 inputs include self-velocity, predator position, predator velocity, neighbor position, neighbor velocity, and neighbor's food predator intensity. This value is like a signal value that agents give out to neighbors to tell them the estimate proximity of where food and predator is. For example, when one agent sees food, this value may be set to a maximum value of 1. But for the neighbor agents that don't see that food, they will have no information of where the food is. But they can actually observe this value of their neighbors, right? So if their neighbor has this food intensity value of 1, other neighbors can know that, oh, this agent sees food, right? So this intensity signal value. And the last one is the Raycast Sensor. All of these inputs combine to a total of 194 inputs. We input these values into the neural network, And the neural network will compute and output two actions. The first action is the turn force action. This value will determine whether the agent will turn left or right and how sharply or how strongly the agent will turn. And the second action is the swim speed. This output determines the acceleration or deceleration of the agents. All inputs and outputs are also normalized to the range of -1 to 1. Now, for the predator design. The predator has 5 major properties: velocity, position, and radius. These 3 properties are similar to our prey fish, but we've added a stomach counter and a hunger switch for the predator. Each time the predator eats a fish, its stomach will be increased by 1. The predator can also move in the same way that agent fishes do. Like they can steer left and right, or they can accelerate and decelerate. The predator speed is also capped to a minimum speed and maximum speed. They can also see the world the same way our agent fishes do, by raycasting. But for the predator's raycasting, they can only see obstacles. And they can also use radar scanning to scan for prey fish. When the predator eats a fish, its stomach increases by 1. And when it eats enough fishes so that its stomach equals max stomach, its hunger switch will be set to false and its stomach will start decaying. So this process is similar to digestion, right? Their stomach will start decaying until the stomach becomes 0, and then hunger will be set to true, and then they will start finding more prey to eat. Okay, so the predator does not have a neural network brain, right? Because the aim of our project is to simulate prey fish schooling. So for the predator, we hard-coded the logic of swimming into the predator. So the predator makes decisions from 2 states. It can be hungry. It can be either hungry or not hungry. If the predator is not hungry, it will cruise or it will swim randomly. But if the predator is hungry, it will check first if any prey is visible. That means if any prey is in its scanning radius. If there are no preys within the scanning radius, it will also swim randomly. But if it is hungry and there is a prey visible, then the predator will start chasing that prey, right? So it has 2 states that map to 2 decisions. For the cruise mode, we capped the predator's speed at a V cruising speed. And the predator's steering is randomized using a Perlin noise function. So a steer here is the steering acceleration of the predator. The steering acceleration we calculated by inputting the predator's X and Y positions into the Perlin noise function, which outputs a value from 0 to 1, right? But we actually need this steering acceleration to be able to make the predator steer left and right. So we multiplied the output from the Perlin noise function, multiplied it by 2, and shifted down by -1, so that the randomized output number becomes a range of -1 to 1, right? And we multiplied that number, output number, by using this variable, which is the steering force coefficient that determines how sharp the predator will turn. And then multiply that value by the normalized vector perpendicular to the predator's current speed, which is steer direction. After we got this random steering direction, we add that acceleration, multiplied it by delta time, and add it to the predator's current velocity. Okay, so now for the chasing mode. In the chasing mode, the speed of the predator is also constant at v chase. V chase, the velocity of chasing must be faster than the cruising speed because the predator wants to get to the agent fish faster. And for the formula of the chasing velocity, we take the vector from the predator to its closest prey, and then getting the normalized direction of that vector, and then we multiplied it by the chasing coefficient, which determines how sharp can the predator turn to follow the prey fish. And then we also multiplied this value by delta time and added back to the predator's current velocity.
So next, we will talk about the algorithm used to train the neural network of the crayfish. So we use deep reinforcement learning to adjust the weight and the bias of the crayfish. Deep reinforcement learning is simply use reinforced learning to tune the weight and bias of the neural network. The agent or the crayfish have to take an action to the environment. Then the environment will set the reward for the specified action, and we can use that reward to train at the loss in the neural network. In the Unity simulation, we have ML agents or a built-in reinforcement learning library. We use ML agents as our backbone to train the model. The algorithm we use is proximal policy optimization or PPO. Proximal policy optimization is basically the policy gradient algorithm. It works by accepting the input at a state of the current observation that the agent receives, then output the probability of the action we will take. We will use the highest sampling, the best probability to use and act as an output of the neural network. The reason we use proximal policy optimization is because we compare our two algorithms of the reinforcement learning. First, reinforcement learning have two main types of algorithm. The first one is the value function and policy gradient, and the second one. The value function works best in the discrete workspace. It works by accepting input as the current state and the current action, and it will output the reward of that state and the action. This type of value function did not scale well with the continuous action space because it needs to have a table of state and action of all possible combination. If we want to work with the continuous action space, we should use policy gradient in it. So our policy gradient only takes state and output probability of action. Our proximal policy optimization lies in policy gradient algorithm. And if we compare the policy gradient algorithm in the next slide, we have two main types of policy gradient algorithm. The first one on the left is the policy gradient one model. The second one on the right is the actor critic model, or we have two main models. The first one is the actor, the second one is the critic. We have to train the actor and have the critic scores its reward and use that critic to train the actor again. So actor critic model is more harder to train and have slightly better performance. In this case, we will focus on the policy gradient model, which is acceptable performance and a lot easier to train the model. If we compare all of the algorithm in the table, we can see that if we want algorithm that is supported by ML agents library and is policy gradient, critic free model, and works with continuous space, PPO lies in the end. So that's why we choose possible policy optimization. So next, let's look at the reward we use to input in the algorithm. This is the benchmark we get from the policy gradient paper. We can see that policy gradient has the comparable performance to the actor critic model. Why it's a lot easier to train because it's only have one model, not two like the actor critic. And next is our reward design. So the first reward that you give to the agent is a positive reward when the fish add or collide with the food balls inside the food areas. Another one is a negative reward to encourage agents not to collide with each other. So when agents collide with each other agents, it will have the negative reward as a feedback. And another one is collision negative rewards. But this one is when the agent collide with obstacle. Another reward is a predator distance reward. It's inverse proportional to distance. It will be given when the predator came close with the agent scanning radius. So this will encourage the agent to avoid the predator at all costs. And of course, when the agent is eaten or just collide with the predator, it will get a significantly negative rewards. And the last one is a never lost reward. This reward is used to encourage the schooling or grouping behavior of a fish. If the fish cannot see its neighbor in the scanning radius, it will consequence in a negative rewards continuously to the time. And that is all of the reward used in turning the algorithm. So if we can see all the parameters used to tune the reward inside our report. So apart from all of the reward we use to input into the model, we also have another reward. It's called intrinsic curiosity reward. So why we need this intrinsic curiosity reward? First, we have to talk about the sparse reward problem. So there are some cases that the reinforcement algorithm cannot handle large action space, like playing games without receiving the reward continuously. So in some games like Mario, the reward maybe can only set that the agent be able to not be able to pass the current state. And during the playground, the playthrough of the game, we cannot give the reward implicitly or explicitly to the agent. And that makes agent only have a feedback when the game finishes. This also applies with our fish schooling problem with the foraging behavior, because fish don't know how to explore the area and find the food area that is randomly spawned through the map. So our behavior at first is that fish spawn and just explore a very little bit and cannot move to the area that have food and eventually die. So we think if we add another reward that's encourage exploration to the fish, it would be good to have fish explore more. So what intrinsic curiosity reward work is a reward that encourage the action that is uncertain or the action that encourages exploration. It works by creating a model that input at the current state and the action. And from the current state and action, it will try to predict the next state from the current action. If the next state the model predict is correct, this means that action is very normal action and it will not encourage exploration at all because it's very easy to predict. So the reward, intrinsic curiosity reward will be very low. But if the state it predicted is not true, that means that action is not very predictable. So it's very worth to explore that action. So it will increase intrinsic curiosity reward. We can see from the intrinsic curiosity reward in their paper that with the intrinsic curiosity reward and with sparse reward problem like gaming, we can turn the model from not learn at all to the state and it can perform efficiently. So next is our experimentation setup. So we train a model 2 million time step. We train it about 40 minutes. So we have to tune the hyperparameter many times to get the best result for our best model. And each time it takes about 40 minutes to train. We train it only on CPU environment on the Intel Core i7 6700K with 32 GB of RAM. And let's look at the discussion of the result of our model. So first, I will talk about schooling behavior. So we get a really excellent schooling result from the Unity simulation. However, in the rare case, some fish cannot regroup with the main group and just lost during the swimming. And our reward we use to train the model, we still need implicit negative reward to encourage fish to form schooling behavior. So we think further study can benefit from removing this reward and try to use or adjust hyperparameter and train another model that the fish can learn to do a schooling without this negative reward. And for the foraging behavior, we also get the excellent result. The fish can accurately and get the food from the food area efficiently. However, we can see that from our current simulation, the fish will always hungry and eat all the food as possible. So it's like it's not really correspondent with the nature behavior. We think if we add hunger level and stomach level to the fish and adjust this hyperparameter more, we may get the better result for the foraging. For the predator evasion, we think this result is more challenging one. We see some of the fish that fails to avoid the predator at all. And since predator have two states, chasing state and cruising state, when the predator is not hungry, it will always be in cruising state. And we find that when predator is in cruising state or not the hungry state, fish will view the predator as not a threat at all, and it will not try to avoid the predator. And in that time, the predator can accidentally eat the fish easily without evasion at all, but it's a rare case. So in most cases, fish is still try to avoid. So next, let's look at the demo of our application.
Giờ share ต่อให้เลยไหมคอปเตอร์
จะให้มอน
เดี๋ยวแชร์ต่อให้เลยไหม
โอเค
โอเค
All right, okay. Screen is visible for everyone.
Yes.
Okay. Let's so here's the simulation. So as you can see, maybe not as clearly right now because it's still in like the initial state, but like, yeah, the fish should start to form a school. Here we have like a number of school, a number of groups of fish. So that's like the schooling behavior. Let's see the school. And the next behavior that we implemented the food foraging behavior. So there we go. It's getting the food. And after the food is depleted, it should regroup into the school as normal. And the third behavior is also the predator. So right there, let me make things a bit quicker. Let me move the predator.
Predator อยู่ใน fish tank
Okay.
ต้องเปิด fish tank ออกมา
Just to make things a bit quicker, let me. So here you can see that the fish will react accordingly to the predator. That is like they try to move away when they detect the predator. Let's try with like a big school of fish.
Where are the fish? This one is the predator, right?
Yeah, the orange one is the
in the
predator,
circle.
correct? Looks like I lost it.
Okay. But actually, I cannot see all the play fish. Where are they?
And let me switch to this this view and just follow the predator.
Mm-hmm.
Yeah, the fish will try to like evade this orange predator.
Mm-hmm.
So other than that, the user will have like other controls to interact with the simulation too. So other than the general zoom in and out and moving, panning the camera, we also have like a you can also decrease or increase the simulation speed. So here we go. This is pausing the simulation. We can like slow down or speed up. We can, as you have seen before, we can follow like let's say this fish in particular. We can just click to follow the entity. We can also do the same with the predator. And if you want to follow like a school of fish, we can also right click and drag, and we'll follow like the average position of the selection of these fishes. The user can also interact directly with the environment by spawning obstacle blocks. These blocks can be moved and placed wherever by the user, and the simulation or the fish will react accordingly to the this obstacle that has been placed. Let me play the simulation. And some of them might hit, but like most of them will be able to react in time and like move away from the obstacle. So yeah, that's pretty much our simulation.
Feel free to ask any questions ครับ
Okay, ครับ I think it's nice. And I just saw something like the input of the neural networks that you use is you use the I'm not sure, or it's like the location. Can you go to show me the slides relating to the inputs of the networks?
Yeah, sure.
Okay, I'm stop sharing my screen and take it back to Mon.
Wait a second, the slide. Should be this page, right?
Yeah. Okay. So it's like the location of the predator, the neighbor position, velocity, intensity, right? And I'm not sure. This one is like you put it in the reinforcement learning environment, right?
Yes.
Okay.
It's the
Okay,
input
so-
to the neural network. It's just the fish's, the agent's observations of the environment.
Okay. So I'm not sure that so the position, the velocity, and the first question in my mind is like do we have any like normalization for each input to make them
Yes.
Okay.
Yes.
So you
all
normalize it
inputs
already, right?
are normalized to the range -1 to +1.
Okay, great. And how, for example, I'm not sure that it's like how about effect of the position. For example, if the coordinate is in real number, right?
Yes.
Okay, so the velocity is also show the sign of the velocity, show the direction, right?
Yes. Yes.
Okay. So I'm not sure. Maybe the distance, from to the predator or the distance to the neighbor in X and Y, maybe may be able to help. I'm not sure. Because I think that the position cannot help.
It's a relative position.
Yes,
Oh,
it's relative.
okay.
Everything is relative,ครับอาจารย์
And it only will get input if it's in a radius that our fish can sense.
Okay. So
Right.
if it's relative, it's fine. ครับ
ครับ
sorry that I missed that point. Okay. ครับ so I think it's nice นะครับ I have no question ครับ
ครับอาจารย์ดวงดาว do you have any question ครับ
ค่ะโอเคค่ะif you talk about the relative positions, so if I have many neighbors, will the value affect or it will be just turned into 48? I'm just not sure about this.
I couldn't hear you clearly ครับอาจารย์ can you come and mute the question again?
About the neighbor position, if I have many neighbors, if I'm a playfish and I have many neighbors and I have very few neighbors, what the difference between them according to the model, the input?
ครับ Okay ครับอาจารย์ Okay.
Hmm.
For our neighboring fish data, we use something that is called a buffer sensor. This buffer can hold a maximum of 24 neighboring fish data. It's kind of like an array that we can add neighboring fish data into, and then we input this array into the neural network hub. And this array can hold a maximum of 24 items. So one agent fish can observe up to a maximum of 24 neighbors ครับ
Okay. So if I observe only 2 neighbors, then the most of the value will be just like the 0 or something.
Yes, it would be 0 ครับ
Mhm. Could you please explain to me about the ICR, because you have a slide that have the intrinsic curiosity reward, and on the right hand side there is a graph, but I'm not sure what does it mean.
On the right
It should
side,
be,
mhm.
it should come from a paper, I guess. On the right side. Actually, you don't have this one, right?
Yeah, it's not our benchmark. It's a
Yep, but
benchmark
next,
that is introduced in the ICR original paper.
right. But what does it mean by the yellow and green lines? Number of trainers.
So in the original intrinsic curiosity reward, it will talk about when some kind of input is have two-dimensional, and since intrinsic curiosity reward is try to predict the next observational state from the current action and state. So there are cases that the observational state is too large. Maybe our case is also too large because it have 192 input observed. In the intrinsic curiosity reward, there also a case that the state is very large, like we use all of the pixels in the environment at a state. So they decided when the state is too large, that we have another network that try to reduce the dimension of the state in the intrinsic curiosity reward module. Maybe I can show you another diagram.
Let me I'm still curious, right? What this graph means, right? Or is it clear to you now?
The yellow and the green.
Okay.
What does it mean?
The y-axis here is, if I'm not mistaken, it's the reward, right? New reward.
It's the reward.
Yes. Yeah. So this y-axis represents the learning rate of the agent's kabajan. So the higher the graphs, that means the more the more rewards that the agent can get. So the blue line here is just what's A2C new actor critica.
Yeah, actor critic.
Yeah.
The improvement of actor critic model.
Yes. Oh, okay. So in this chart, every model uses actor critic, but the blue line is just pure actor critic model, and the yellow and green lines have intrinsic curiosity module attached. Yes. So that means that the actor critic models with intrinsic curiosity modules attached, they can learn much better, as you can see from the rewards gained by number of training steps. So by 9 million steps, the normal actor critic model, you can say that it doesn't learn anything. It doesn't know how to gain more rewards. Compared to the green and yellow models, which have intrinsic curiosity, both of these models can gain 1.0 reward. I think in this place, it means it finishes the episode. It completed the goal. So it got 1 reward by 7 million time step. both yellow and green finished the goal, but the blue line did not learn at all. Yes. Is it clear now?
Yep. Thank you. It's clearer. But then your friend mentioned about this one, the ICR, that in this paper they use about, too many features, right?
Yes.
Because you mentioned that they try to reduce kind of the features as the input or something like that. Did I understand clearly?
Yes.
So what does how this apply in your term project in terms of the ICR?
We use the same implementation as the ICR paper. So in the intrinsic curiosity module, there is a built-in dimensional reduction as using a neural network to reduce the dimension of the state automatically. And we just have to train it.
So you mean that the 100 and okay, so you mean that your input, almost 200 features, some of them will be just removed or just ignore? I'm not sure.
It will be reduced from 192 to the smaller dimension when fitting into this ICR model.
I think it is not like really clear yet. The intrinsic curiosity module is, we used it because we want the agent to try more riskier ways of movement. That means that this intrinsic curiosity module will promote the agent to put itself in states that isn't really, it kind of want to put itself into a state that is not predictable. That means that the current state is ST, right? So this intrinsic curiosity module will reward states that are unpredictable, right? So if we put in the current state and this module predicts the next state, which is ST plus 1, and then when the prediction result is out, we compare that prediction result with the real result, right? The real state, that the real ST plus 1. When we compare the difference between these two and the difference is really great, that means the prediction result is bad. This module will give the reward to the agent, right? But if the prediction result is out and it is really similar to the real next step of the state, the real ST plus 1, if the difference is really really small, it will not give out any rewards. That means it rewards action and state that produces unpredictable results. Yeah, and the input, what should I say? The input dimension reduction method is not for the main PPO model. It does not reduce the input that is input into this neural network. It reduces these state variables that is inputted into the ICM module, just the ICM module, not the main module.
Okay.
Yeah, the reduction is just for state prediction.
โอเคค่ะ โอเคเลย ขอบคุณค่ะ Very interesting work. Okay. And I think you learned a lot.
We did learn a lot.
So in your results, for the last one about the predator evasion, how can you improve? Because you said that some of them, some playfish still cannot avoid to be eaten, right? Do you have some ideas for further improvement?
Yes, we already did kind of improved it after we finished writing the report. So yeah, in the newer version, we just gave a new reward that is a negative reward that, oh yeah, I believe we already did include it in the presentation. It is wait, it is this one, Kap. Right? So initially we only had this reward, the reward that is given, the negative reward or the punishment that is given to the agent when it gets eaten by a predator, right? So it only gets this punishment when it is eaten by the predator. So this reward is called a sparse reward, Kap Ajahn. It's rarely given. So we fixed this by introducing something called
reward.
Yeah, this reward that is given at all times whenever the agent sees the predator, and when the predator gets close, as the predator gets closer to the agent, the reward given will be it will increase. Yes, because the reward is inverse proportional to the distance between the agent and the predator.
If I may add, we found that like we have discussed that primarily, yes, we want the fish to like survive most of the time, but we think that if we optimize it too much and like the fish has like a perfect behavior where the predator like always like they never get the fish, we think that that would result in an unnatural behavior. So because our goal is we want to simulate the school of fish in nature, if like the fish has like a 100% evasion rate, that would be kind of unrealistic.
Agree.
We also thinking
about what?
About increasing the number of predator, but due to our computer performance, we try it, but it don't help because we cannot run the simulation efficiently with more number of predators.
Okay.
Is this one clear, Kavajan? Can you see the fish?
Actually, I see the predator, but for the playfish, it's very small.
Is it bigger now? It's bigger now, Kap.
A little bit more. Okay,
I'll try to drag the predator, and as you can see, the fish swim away from the predator. And it really improved a lot, Kap, after we added the predator distance reward.
Okay, because in that case, the distance reward will be available. I mean, the values will be available for all the playfish that are within the distance, right? I mean, we have more values to be used by the model, because if you get eaten, it will be just rare case, as you said.
Yes.
And only a very few fish will be affected with the value to the model, right?
Yes, Kap.
Okay, very interesting. The last question. If I don't have a predator at all, I saw on a documentary or several documentary, or the fish will have the schooling. I mean, kind of swim together. Do you have something that show like that without the predator? Because I'm also wonder about the nature, right? When the fish swim together in kind of the patterns, different kind of the patterns, or some specific patterns.
Actually, when we first train the model, we first train it with only foraging behavior, and then we train it with the foraging and schooling behavior include, and after that we add the predator and train it.
Work.
So it works. It's worked very fine. I'm not sure we have a checkpoint of that very fast.
We can just remove the predator from this model, and as you can see, Wait a second. I think the scale is wrong. Okay. Okay, so as you can see here, there's only just one group. So if there's no food and there's no predator, they'll just all swim together around the tank like this. I think it's really small, but right here you can see, oh, I forgot we have this feature. Okay, is this clearer, Havajan? We can see the network of fishes here.
Okay.
Yes, and all of them,
Okay.
all 70. I forgot to tell you guys that we have 75 prey fishes here, right? All of them are
very
swimming together in
simplified.
just one group.
ค่ะ
ครับ
Very interesting and very impressed ขอบคุณนะคะ I have no more questions.
Okay, so the papers with you guys, and I think you should share the papers with Ajahn too, so that Ajahn can mark yours. I think the one in ISE submission system is a bit old, right?
Yes.
So
Yes,
I think you should share the latest one.
Yes, I'll upload into Google Drive, and then maybe I can share to Ajahn. ครับ The one in the Moodle is the old version is not updated. ครับ
One, I think we can directly upload to Zoom.
Really?
Or not?
I think so.
Oh, we can, I think. Okay,
You can
I'm
attach the file
yeah.
in the chat box.
I'm uploading the file. ครับ
Oh, but you cannot replace the new one into the Moodle, right?
Yes, I think we
Cannot.
cannot replace.
เหรอ Okay.
So the latest version is in the chat right now. ครับ Can you
The
can
Zoom
Ajahn?
chat box. Okay.
Yes.
Yep. Okay ค่ะ Personally, I really like this kind of the project. It's really creative, in my opinion.
And
Thank you.
I think it's
Thank you.
you've done very well. I think
ค่ะ
you've done a lot of things. Nice work. For downloading the paper, the evaluation form, I think it's quite slow a moment. So how can we submit this form?
I mean, the scoring, you mean, which form?
Or the scoring form, which one?
I think
we have to
just mark it in
evaluate
Moodle.
In Moodle, right? Okay.
Yeah, for the ISE students. Yeah.
Oh, so it's like at first I think that it has another evaluation form, so no worry if it is
yes, it used to
one,
have, but I think they should have included in the system all of them now, because we've done this before, and they couldn't give us the forms last time. So I think they should all be in the system, but I haven't checked.
Okay, so I'm here in the Moodle. So your group's name. Okay. A moment, I'm trying to find it.
Fish schooling.
Okay. Okay, I found 3 of them already. Okay, it says the final report and oral exam, so that's all. Thank you very much ครับ
I think yeah I think that should cover all.
Yes only one click and the report and oral exam together.
Okay, and you guys please send me the link to the document in Word again too.
โอเคครับ
so that I can see if you need to do some refreshing of things a bit more just in case. You can send it to me on Discord.
I already sent the link ครับอาจารย์
Okay I'll have a look again and see if you need any further modification, but most contents are okay I think. Okay so
very good job
well done.
ค่ะ
well done
โอเคครับ
I actually
เรียบร้อยครับ
want you to write some paper out of it, because it seems like a really good project. I'll talk about this with you guys later, so maybe we can submit to some conference maybe that has
Nice.
this kind of topic.
ครับ we'll try ครับ
โอเคครับ
โอเคครับอาจารย์ทั้งสองท่านขอบคุณมากครับ
ครับขอบคุณครับขอบคุณครับ
ค่ะ
พี่ออม
สวัสดีค่ะ
สวัสดีครับสวัสดี
ครับ
ค
สวั
รั
ส
บ
ดีครับ
thank you ครับ
ค่ะ
โอเคก็เดี๋ยวค่อยคุยแล้วกันผมไม่รู้เหมือนกันว่าพวกเราจะว่างพอจะเอาไปเขียนเป็นเปเปอร์ได้ไหมแต่จริงๆมันคือเขียนจากคือเอาจากในรายงานแหละไปเรียบเรียงใหม่ให้มันเหลือน้อยหน้าลง
ครับ
แล้วลองดูเนาะแต่ยังไม่ได้ดูว่าอยากส่งคอนเฟอเรนซ์อะไรกันใช่ไหมยังไม่ได้ดูเลยใช่ไหม
ครับ
เดี๋ยวจะเดี๋ยวจะลองดูให้ละกัน แต่เราดูด้วยก็ดี เราดูด้วยก็ดีแล้วได้ฝึกดู
มันหาพวกนี้ยังไงครับแบบดูว่าจะส่งไปอันไหนดี
มันพูดยากเพราะส่วนใหญ่คงเป็นคอนเฟอเรนซ์ทางคอมพิวเตอร์ไซน์แบบทั่วไปเราอาจจะลองหาคอมพิวเตอร์ไซน์คอนเฟอเรนซ์ลองดูวิกิลองดูวิกิคอนเฟอเรนซ์แล้วหาด้านคอมพิวเตอร์ไซน์ทั่วไปผมว่ามันจะมีให้ลง แต่ก็ดูว่าอันไหนมันจะจัดแถวนี้มั่งหรือจัดออนไลน์จัดอะไรจะได้ไปง่ายคือไม่ต้องไปไงไม่ต้องเดินทางถ้าเป็นแบบจัดออนไลน์ก็ดีไปสมัครต่างประเทศได้ด้วยอะไรเงี้ยแต่ว่าถ้าเป็นแบบต้องไปเนี่ยเราจะดูเมืองไทยเพราะว่ามันจะได้ไม่ต้องเสียค่าเดินทางเยอะ
ครับ
นะลองดูพวกวิกิคอนเฟอเรนซ์ก็ได้วิกิคอมพิวเตอร์ไซน์คอนเฟอเรนซ์อะไรเงี้ยมันจะมีให้ดูอยู่ก็ค่อยดูก็ได้แล้วก็อันไหนสนใจก็ลองมาเช็คกับผมดูก็ได้
ครับได้ครับ
นะมันจะมีตอนนี้ถ้าเป็นเมืองไทยแต่ผมไม่รู้เขาจัดไปยังอาจจะจัดไปแล้วมันจะมีอันนึงที่ตอนนี้กำลังรีวิวอยู่ก็คงไม่ได้ส่งนะคือ JCSSE จะเป็นด้านคอมพิวเตอร์ไซน์กับซอฟต์แวร์เอนจิเนียริ่งอะไรเงี้ยแต่เราส่งท็อปิกด้านคอมพิวเตอร์ได้ทั้งหมดแล้วก็มี ECTI Con ECTI Con อันนั้นจะเป็นทั้งด้านไฟฟ้าแล้วก็คอมพิวเตอร์ก็ส่งได้ทุกท็อปิกเหมือนกันแต่ว่าไม่รู้จักไปยังอันนี้คือจัดบ่อยๆเมืองไทย2อันนี้ที่มีสแตนดาร์ดค่อนข้างดีเพราะอันอื่นอาจจะสแตนดาร์ดไม่ค่อยดีแต่ว่าจริงก็ดูอันไหนก็ได้นะเพราะว่าเราคอยมาดูว่าอันไหนที่เหมาะจะไปเสนองานก็ได้แล้วค่อยไปนะจริงๆน่าเอาไปพูดอยู่เพราะว่ามันมีทั้ง foraging ทั้ง predator อย่างน้อยมันมีอะไรครบเอาไปบอกคนอื่นก็ได้ว่าเราทำ predator เพิ่มไปแล้วมันเป็นงี้ไงอะไรเงี้ย
ครับ
โอเคแล้วรายงานเดี๋ยวผมดูให้อีกรอบนึง
ครับได้ครับ
โอเคแค่นี้ก่อนเนาะ
ครับขอบคุณมากครับอาจารย์
โอเค
ครับ
ครับสวัสดีครับ
โอเคสวัสดี